Okay, I'd like to acknowledge my co-authors from the Diviner team, Ben Greenhagen, who you heard at the first talk this morning, Carrie Donaldson, Hannah, who has an excellent poster up on Diviner compositional data, and David Page, the PI of the Diviner mission. We're talking about dark mantle deposits, pyroclastic deposits. One of the major examples is shown here, the dark mantle material at Taurus Littrow, adjacent to the Apollo 17 site. Hoping to sample this was actually one of the many motivations for going to this site for Apollo 17. There are, in fact, many dark mantle deposits on the moon. These are some of the ones mapped on the far side by Jim Head back in the 70s. And they are widespread. They are optically thick. In many cases, they seem to be reasonably smooth, the kind of places where you might want to actually do spectroscopy. These are understood to be widespread deposits of submillimeter pyroclastic glass from eruptions that might have looked a little bit like this, minus the Ohiolahua trees in the foreground. But the product of lunar fire fountain eruptions, and significantly, back in '86, John Delano identified 25 distinctive compositions of these submillimeter glass beads in Apollo lunar soil samples with significant compositional range, all the way from the very high iron orange and black glasses seen at 17 to the green glass that was seen at Apollo 15. The source deposits for most of these have not been identified. I'm suggesting that with Diviner we may actually have the capability to narrow down and hone in on the source deposits of some of these. The Apollo 17 orange and black glass, particularly seen on the surface and in cores at Shorty Crater, are understood and have been understood for a long time to be samples of the Taurus Littrow deposit. The orange and black glass are isochemically identical and reflect differences in the degree of crystallization that are reflective of conditions within the eruptive plume. Pyroclastic glass beads are interesting from a lot of points of view in lunar science. These are some of the deepest sources and most primitive basalts recognized on the moon. The work recently, particularly first by Alberto Sol, demonstrating that there's water in these glasses, is revolutionizing our understanding of the volatile content of the lunar interior. And from a resource point of view, the iron-rich pyroclastic glasses are shown to release the highest percentage of oxygen of any Apollo soil in high-temperature hydrogen reduction experiments. And these things have been cited for a long time as deposits for promising lunar resources. So the question is, can the compositions of these dark mantle deposits be estimated from orbital observations? Ben Greenhagen showed this introductory slide about Diviner and the work that we do in the compositional section of the Diviner team concentrates on the 3/8 micron bands that were chosen actually by Ben to span the Chris-Johnson feature, which is sensitive to polymerization in silicates, and as pointed out by a number of people, including Paul Lucy, ought to correlate reasonably well with FeO abundance in lunar materials, given the restricted compositional range of lunar rocks and soil. We, a couple of years ago, looked at what we believe to be representative soil samples from the 6 Apollo sites, particularly looking at the 20 to 45 micron splits, and where the petrography and the composition have been detailed in the work of the Lunar Soils Consortium led by Larry Taylor. And to get a Diviner footprint representative of the Apollo sites, we looked at an area in 1 by 1 kilometer blocks around each Apollo site, taking the mean of a number of Diviner observations. The diviner footprint is shown here, and averaging them and using the most recent corrections that Ben Greenhagen discussed in his talk. It's also worth noting that even in a nice, flat, smooth place like Apollo 15, shown in this L-Rock frame, there is a certain amount of diversity and basically noise for this work within the 1 by 1 kilometer block caused by impact cratering on a surface that's smooth enough where people could actually land. But looking at the ground truth, the FeO abundances in specific lunar soil samples representative of the sites, and the orbital Christiansen feature average values over 1 by 1 kilometer ranges around each Apollo site. These are the values that we're using. This is the plot of orbital CF, Christiansen feature maximum location on the horizontal axis, and laboratory defined iron weight, FeO weight percent on the vertical axis. And certainly we see a correlation across the range of the 6 Apollo sites between iron abundance and CF. So the question is, can we extend this to the pyroclastic deposits where to give us an additional point of ground truth? Here's the Taurus Littrow deposit again. Here are a couple of diviner frames overlying that deposit, and there is a significant difference in the stretch, basically corresponds to CF values, between the diviner strip going over the pyroclastic deposit and that going over the adjacent Mare area. The average maximum CF value for the dark mantle deposit at Taurus Littrow is 8.41 microns. Dropping this in as an additional piece of ground truth into the former table, we see that even when you extend up, you are now running on reserve battery power. I hope you can do something about that. Because I can't. When you drop that onto the same line and draw a regression line through it, you see that we can, in fact, now take this regression between CF and FeO through the entire range of compositions that we see at the Apollo site, including the pyroclastics, with an R square of 0.9. One other thing to point out, the brackets at the top show the compositional range of the pyroclastic glasses as analyzed by Delano. So we're proposing to use this correlation of CF to FeO to estimate the composition of unsampled pyroclastic deposits. The first one, as I reported at LPSC, is the Sulpicius Gallus deposit on the western side of Serenitatis. Here's an image showing that this deposit is not quite as obvious optically, but certainly has been mapped since Apollo days. Diviner swaths going over it show a fair degree of variation across that deposit. This is an area right at the Mare Highland boundary, and we see a lot of that variation due to impact craters. Maximum CF value of 8.37 microns shows that it's still within the range of sample pyroclastic deposits, but significantly lower values, lower FeO, lower CF than we see at Taurus Littrow. Most recently, we're looking at the Aristarchus Plateau, the poster child for big pyroclastic deposits. Here's a Clementine UV-Vis image. Everything in bright red here is is understood to be a pyroclastic deposit that spans the flow. And we looked at a number of places. The point here is where we took our values, and the CF value for this point on Aristarchus is 8.40, essentially the same as we see at Taurus Littrow. So there are the 3 points that we have analyzed at this point. Sulpicius Gallus and Aristarchus are lower in CF value and possibly lower in FeO than the one at Taurus Littrow, but we certainly seem to be on the way to having a capability to analyze these pyroclastic deposits across the moon, to estimate their FeO contents, and also to estimate the variation within each of these deposits. So the results at this point support the use of diviner CF values to estimate FeO deposits among lunar pyroclastic glasses. And we also realize that the correlation of CF to total FeO for the entire range of lunar samples potentially provides a new and independent estimate for iron abundances across the entire moon. Thank you.
We have time for some questions. You answered all of them. You answered all of them. Oh.
Yes.
So, did you use this new data set to get any hints as to what these pyroclastic deposits might be? I think you
Haven't been looking for that, but
Repeat the
oh,
question.
excuse me. Dave Kring asked, looking at these data sets, do we have any indication of where the vents for these deposits might be? We have not been looking at that at this point. There is certainly now a number of different data sets with increasing resolution going all the way up to LROC that ought to be able to